Hey everyone, welcome to our second lesson in Unit 6. Today we're going to be finishing up talking about the periodic table and the properties of different subgroups within the periodic table itself. So by the end of the lesson, you should be able to describe the different groups of elements on the table, as well as their specific properties for each of those groups, and also be able to describe the states of elements at standard temperature and pressure. Basically, what state of matter would we find in elements on the table at standard temperature and pressure, and they're surprisingly aren't all in the same phase. A little bit more on naming elements, which we kind of ended with briefly in our last unit. We were talking about naming ions. Naming elements, they're relatively straightforward. Some of them look a little bit different, but we don't really have to follow too many rules to name them. For the most part, we're going to find the names directly on the periodic table or on table S. But there are going to be a few where we are going to have to add a few things in order to fully realize the actual name. Now, a few of the more difficult ones to memorize, well, they're difficult because the name comes from the traditional name and has been used since antiquity. Since forever. So some of them are going to look a little bit odd. And the odd ones, sometimes the name doesn't quite line up with the symbol. And those are the ones that are using the older version of the name. Like antimony, which is abbreviated, or its symbol is SB, for English version stibnum. Iron, we also see the symbol Fe for the English name ferrum. We often see things that are iron containing as ferrous, or we might see ferric. That's indicating that something has to do with iron. Aurum, argentum, hydrogerum, plumbium, one of my favorites, which is the antiquated name for lead. Kalium, which is where we get the K for potassium. Cuprum, wolfram, my favorite element, tungsten. Stannum, and natrium. So a few of these really all metals, names stemming from their previous English version. Now, to review how we name ions, we have two simple rules. The positive ions are going to retain the name of the element. The key here with this is that if the atom can form more than one ion, then we have to designate the charge of the ion with a Roman numeral. And I've given you guys some basic symbols for Roman numerals in your notes. And we're going to place that Roman numeral after the ion name, which will signify the charge on that ion. And this is what we call the stock system. For example, Fe plus 2 is going to get a Roman numeral 2 because iron has multiple oxidation states. It can be plus 2 or plus 3. And we want to identify that we're referring to iron plus 2 by using the Roman numeral 2. Since aluminum plus 3 can only have one oxidation state of plus 3, we don't have to write in that it's aluminum 3. Since it can only be in one oxidation state, we'll always assume that it is aluminum plus 3. And I will like to emphasize that if you were to write aluminum 3 with the Roman numeral at the end, I don't necessarily think it's wrong, but it is not really required or even common to write it in that way. Now, negative ions are named after the element, where we replace the second syllable with the suffix IDE. So oxygen, regardless of if it's a -2, -1, or another version, as long as it is a negative ion, we're going to take the first syllable, which would be ox here. We're going to drop the end of it and add IDE, so oxygen becomes oxide. Nitrogen becomes nitride. Now, as we move into the periodic table, we're going to be taking a look at a few different groups, and some of these are easily identifiable on the table based off of the shape of the table. And we're going to go through the chemistry of each of these subgroups and talk about that briefly. One of the ones that we won't focus on too much, at least in the sequence of this class, is this group right here, which is groups 3 through 12, which is what we call the transition elements. Now the first group we'll look at are the alkali metals, and this is group 1. Going back to here, this is going to be group 1. Remember, groups run top to bottom. So these are our alkali metals. And we see that from the key on the bottom here. Now, characteristics of alkali metals is that they all have one valence electron. Group 1, one valence electron. So their ion charge is going to be +1 for each of those elements. They are extremely reactive, and because of that, they're never found by themselves. They're found only in compounds combined with some other element. We can then extract that pure element from the compound using electricity, which we use to kind of break apart the bond between those multiple elements, and then are able to isolate the particular element that we want to use. Now these react violently with water to form hydrogen gas, and a base, an alkali, actually means base. This is why one of the strong bases that we use is sodium hydroxide, which is a strong base and would have been formed by, or the base would have been formed by sodium reacting with water to produce the hydroxide ion, which is going to indicate that we have a basic solution. We get into more of that later in the year. Now group 2, so the group just to the right of group 1, going top to bottom, are the alkaline earth metals. Each of these elements are going to have 2 valence electrons because they're in group 2, and therefore have an ion charge of +2. And they can pretty much only have a charge of +2. So all of our group 1 and group 2 elements, if we're naming them, are never going to have the Roman numeral because they only have one oxidation state. They're also very reactive, and again, found only in compounds similar to group 1. We can extract them from compounds using electricity as well as chemical reactions. And similar to group 1, they react quickly with water to form hydrogen gas and a base. So it's very similar to group 1. The names are even very similar, so be careful with those two groups. Groups 3 through 12 are known as the transition metals. This is kind of the sunken portion of the table. So groups 3 through 12. It sits lower than the other groups, and they have specific properties. One, each of the elements in that transition block are going to fill a specific sublevel, which is why they are kind of separated from the other groups. And I know we don't really get into sublevels, but that's really the reason why they are different and set lower than the other groups on the table. Looking at each of those elements, they have a variable number of valence electrons. It's not specific necessarily to the group that they're in. So as far as the group number correlating to the number of valence electrons, it's really applicable for groups 1, 2, 13 through 18. And we'll get more into that in a minute. But the elements in the transition block can have ion charges ranging from +1 to +7. It's really going to depend on what that particular element is going to be bonding with. And they also have a range of reactivities. Some are more reactive than others. You can have something like zinc that's highly reactive compared to something like gold that is very unreactive. And some of these metals we can find in pure form like gold. Other metals, maybe like aluminum, cadmium, zinc, we're not going to find in pure form because they are a little more reactive and like to react with other elements. Now, a lot of these ions in the transition block are colored, so we are able to identify certain compounds that contain these transition elements just by the color. For example, when we use copper sulfate in lab, this has a blue color because copper has kind of a blue-green hue to it, which is why the Statue of Liberty is its green color. And it's really going to depend on the charge of the copper, whether it's going to be a +1 or +2 ion, that's going to kind of lend it to its blue or green color. And then depending on the concentration of either of those, we're going to get more of a green or more of a blue color. But that color is indicating the presence of copper and is also similar for many of the other transition elements. And any elements in this transition metal block, we are almost always going to be using the stock system, where we have to put in our Roman numerals to indicate which charge we're talking about or which oxidation state we're talking about for the ion, because they have multiple charges. Now jumping over to group 17. Group 17 are known as the halogens. And in group 17, and this holds true for group 13 through 18, if we look at the last number in the group, that's going to tell us how many valence electrons for each of those atoms in that group. So group 17 elements all have 7 valence electrons, and in order to obtain a stable octet, they all need to gain 1 electron, which means they end up with an ion charge of -1. Now these are also extremely reactive and corrosive, so we're finding extremely reactive elements in groups 1, 2, and 17 so far, and these are only found in compounds. Similar to groups 1 and 2, they can be extracted from compounds using electricity to break that bond and separate and isolate the pure form of the element. And these also react violently with metals to form different halide compounds like sodium chloride, which after it's formed is very stable. And that's the reason why these reactions occur, is in order to get to a more stable energy state. Now going into group 18, these are the noble gases. These are relatively more common. Each of the elements in group 18 have 8 valence electrons. They have filled their stable octet, which means all the noble gases, since they have the stable octet, they don't want to bond, and they are completely non-reactive. They're never found in compounds. Xenon and krypton can be forced to react with fluorine in the lab, but it is not naturally, or they are not naturally reactive. They have the stable octet. They don't want to bond. They're not looking to exchange electrons with any other element. There's also another unique property to the noble gases that we'll get to here shortly. And these gases, you can see in the, what we would call, I guess, neon lights below, these all can be filled with different gases of different elements. And as we saw in last unit, if we send some electricity through these tubes, the element, depending on which element we're using, will give off a signature colored light. And again, if we were to break down that light through a prism, we would see the bright line spectrum for that element. Now, as far as element phases, these have to be memorized. And it's really not too bad, but all elements at 25 degrees Celsius are solids. And that's everything that's green on here, except for the ones that are in blue and yellow. So once again, these are all solids except for 2 liquids that we see in blue, mercury and bromine. And again, this is at room temperature. All of these elements can exist as a solid, liquid, or gas depending on conditions of temperature and pressure. So those are our 2 liquids at 25 degrees Celsius. The gases are going to be all of group 18, which is all of our noble gases. Gases right in the name. And then there are 5 others. Hydrogen hiding over here, nitrogen, oxygen, fluorine, and carbon. Those are going to be all of our elements that exist as a gas at room temperature. Again, we can have liquid oxygen, liquid neon, or solid neon or oxygen, or any of those for that matter, as long as we have appropriate temperature and pressure. Now, allotropes, this might be more familiar than you think, but an allotrope really is a different form of an element. And it really just depends on the conditions of their formation, what the conditions were like when they formed. And a good example of that is diamond. Now, soot that you might find in your chimney or on a log after a fire is the exact same thing that you would find in a diamond, but they are formed under different conditions. Diamonds need high temperature and pressure and a lot of time in order to form and create their covalent network structure, which makes them the strongest substance that we know. There's also several other forms of carbon that just contain carbon atoms. Fullerene, also known as buckyballs or lubricants. Graphite, also used as a lubricant. All of these just contain carbon atoms, but they look very different and they have different properties, and that just depends on the conditions that they were exposed to when they formed. But these are all allotropes of carbon. There's also 3 different allotropes of oxygen that we'll take a look at, and these ones you're going to need to know as well. We can have atomic oxygen, just one atom of oxygen, it's still oxygen, or O2, which is one of our Brinkelhoff elements, so we actually always find oxygen diatomically. So this is an oxygen molecule. These would have different properties from each other. We actually breathe diatomic oxygen. Oxygen is really reactive. We never really find oxygen as a monatomic molecule. Ozone is also just oxygen, but it contains 3 oxygen atoms. So they all contain the same substance, just a different number of atoms in that particular molecule. But ozone, which I suppose we could breathe, although it's really contained in the upper atmosphere, is similar to diatomic oxygen and similar to atomic oxygen, that it contains only the same element, but ozone is not going to satisfy our cells for respiration. Only diatomic oxygen will. So each of these are going to have different properties, and ozone really is formed in the upper atmosphere, and that's why we see it, or we don't see it down near Earth, and we see more of diatomic oxygen as that's being released from plants and held more towards the surface of the Earth. Now, molecules are different than compounds, and when we get into bonding in our next topic, this will become a little bit more clear. But molecules, it's a particle, kind of like a compound, but it's made of nonmetal atoms that are covalently bonded. And we'll learn about this specifically in our next topic, but they're covalently bonded together. They're essentially one part of each other now. The number of atoms of each of those elements in the molecule are consistent from molecule to molecule. This is why waters always have a ratio of 2 hydrogen to 1 oxygen. That's why we get H2O, a 2-to-1 ratio. And every water molecule is going to have that ratio. And again, those hydrogens are covalently bonded to the oxygen, which means this entire molecule is one piece. The orbitals here that contain these bonded electrons are essentially one part of the molecule now. Now we can also have monatomic molecules, and these are going to be all of our noble gases. They only exist as monatomic molecules, and they're called molecules because, well, they don't react with anything else, so we just consider themselves molecules. But they have a full valence shell, which means they're not going to bond to anything, and they only exist by themselves. Remember, mono means one, so we have one atom molecules. That's a monatomic molecule. So diatomic, di meaning 2, is going to be a 2-atom molecule. And these are going to be our Brinkelhoff elements. All of our Brinkelhoff elements are diatomic, meaning that we have 2 of the same atom bonded to itself. And these elements, which are found free in nature, are very reactive, so they tend to react with themselves. So a chlorine, when coming across another chlorine, will try and bond at an open spot here, looking at our Lewis dot diagram, and become a Cl2 molecule. And we have a covalent bond in the middle. Same with the hydrogen. Looking to fill its valence shell of 2 electrons. These come together, and we end up with a bond between the 2 and a molecule of H2. Try and keep it clear that all of our Brinkelhoff elements are always found diatomically, and we always write them as Cl2, H2, F2, O2, and so on. We never write them as just Br. It always has to be Br2. If you guys have any questions, make sure you write them down and come see me and get them answered. Hope you all have a great day.